Okay, so anytime we talk about a rate, generally we mean how something changes with time. That's almost always the case. Anytime we talk about a rate of change, that we're always talking about how something changes with time. So a flow rate then will refer how a flow of fluid changes with time. And in particular, we're looking at a change in volume over time. So this flow rate, which we're going to call Q, is going to be defined as volume divided by time. So Q then is equal to capital V divided by T. In a pipe, the flow rate, to have a closed pipe, the flow rate must be the same in different parts of the pipe. So this is based on the assumption that fluids are not entering or leaving the system. So imagine I have a pipe here, and let's just say it's all the same cross-sectional area, so it doesn't change with as you proceed through the pipe. If here I have a flow rate equal to 1 cubic meter per second, that means at a given point, I have a cubic meter of water will pass, or whatever my fluid is, will pass by that point in 1 second. That means that over here, I also have to have 1 cubic meter per second. That's always going to be the case, that the volume flow rate has to always remain the same. And as I said, that assumes that I'm not getting any fluid going into the system or going out of the system. Because say, for example, I have 1 cubic meter per second here, but here I have a half a cubic meter per second. That would mean that somewhere along the way, I'm losing a half a cubic meter per second. This is based, by the way, on the conservation of matter in a general sense. That is, that matter cannot be destroyed or created. And we can express this in an equation by saying that Q1 has to equal Q2. So if my Q1 is here, this is my Q2. Those two have to be the same. This is going to be V divided by T equals V divided by T. I'm going to call this V1 and we'll call this V2. Now, you remember we said that volume in general is an area times, we said height, but I'm just going to call it an area times a distance. So like if I have a cylinder, the area is right here. That's my area A, and if I want to know the volume, I multiply it times the length of that. So it's going to be the volume we equal to area times height, and then that's how we find the volume of a cylinder, or really any three-dimensional object. So I can say then that I can replace my V's here, my volumes, with areas times distances divided by T. I'll call this A1 D1 A2 times D2 divided by T, and then recognize here that this ratio, or this distance divided by time, is a speed. And so that gives us the flow rate equation, or it's sometimes called the continuity equation, which is that A1 V1 equals A2 V2, because my D1 over T becomes V1 and D2 over T becomes V2. Now, what this means in practice is that let's say that I have a pipe that's not the same dimensions, that it starts out big and it ends up small. I know that Q here has to equal Q here. However, this is A1 V1, and that has to equal A2 V2. As I move into this smaller section of pipe, A2 gets small. However, the product of A and the velocity, V, still has to remain constant. It still has to be equal to that. So if the area, A2, is smaller than A1, that means that V2 must increase. You can sort of think about this, that here I'm going to have a velocity that's small, and here I'm going to have a velocity that's big. Have you ever used a garden hose? If you have a garden hose and you put your finger over half of the hose, what you're doing there is that you're decreasing the area so that the velocity will then increase. And so that's a great application of the equation of continuity. Let's take just another second. We're going to do an example. If a pipe has a cross-sectional area of 20 square centimeters and water flows with this speed, what is the flow rate in the next pipe if it gets smaller to 10 centimeters squared? I'm going to draw a picture here. It helps us to think about it. All right, so I start at 20 centimeters squared. That's A1. A2 is 10 centimeters squared. V1 equals 30 centimeters per second, and I want to know what is V2 equal to. So I start with my equation of continuity, A1V1 equals A2V2. Or first of all, I can just think of this. Well, I know that the velocity has to be going up because my pipe is getting smaller, and it has to be going up by the same amount that the area is going down. So the area is going down by a factor of 2, so the velocity has to go up by a factor of 2. All right, if you can see that, that's wonderful. That's really the best way to do this. But if not, let's just use this equation. As you know, I'll give you all the equations on for various quizzes and exams. I have A1 is 20 centimeters squared times V1, which is 30 centimeters per second. By the way, that gives me a flow rate of 20 times 30, or 600 cubic centimeters per second. And I have to always have 600 cubic centimeters per second flowing through this pipe. That's going to equal to A2, which is 10 centimeters squared, times the velocity 2. So 600 divided by 10, V2 is equal to 60 centimeters per second. But I knew that because the area decreases by a factor of 2, so the velocity increases by a factor of 2.